Hey guys, Mr. Newman here with what will hopefully be a pretty quick video. We just did integration, just getting you started with antiderivatives, and you have a bunch of rules that you now know. But often we are left with much more complicated situations where we have to use something called U substitution. So our goal throughout U substitution is to replace a complicated integral with a simple one, okay? So we want to turn it into one of the things that we know how to take the integral to, because a lot of these, as you look down here, we actually don't know how to. And I want to give you a brief overview. Is what we're really doing here is we're really doing the chain rule in reverse, okay? But I have a few steps to make it a little easier for you. And yes, I think I've mentioned this before, but in general, doing integration is more difficult than doing derivations or taking the derivative, right? So whenever we're looking at chain rule is pretty straightforward. Doing the opposite of chain rule, you have to do a little bit of magic to work backwards and set it up correctly. And it doesn't always work nicely, as you'll see here, okay? But this first video, hopefully this goes by quickly. These are the 6 steps. First, you're going to choose a u value, or sorry, choose a function or value to replace with your u, okay? And then what you'll do is you'll take the derivative of both sides, and you'll get du equals the derivative of the other side. And what you're going to want to do there is you're actually going to want to, I think I have this written actually, you're going to want to, I'll share this with you guys, you're going to want to solve for dx, okay? Because if you solve for dx, it gets, I think, a lot easier when going back and plugging back in, because the next step is you're going to rewrite the integral in terms of u, so you should have no x's at this point, okay? So a little thing, if you do have any x's, that's where you'll have to pick a different u and try a different u. So notice down here, sometimes say you have to be insightful and have perseverance. That's because if you pick a u that doesn't work, sometimes you'll need to pick a different u, and that's where you see this on step 3, okay? So if it happens, it turns out that you do have x's left over, go back and try a different u, okay? Then you'll find the resulting integral, so you'll integrate it because you have it, and hopefully in terms of something that you can do. And then you'll replace u with your function again and find it back in terms of x. So you can't answer it in terms of u, you need to find the original function back in terms of x. I will warn, this is the most forgotten step, thing that students most forget, so watch out for that, just remember to do that. And then you just want to check by differentiating, and at first we'll write that down. Hopefully after a little while you can just kind of check by eyeballing and seeing, okay, yes, that's how you get it. So I said choose a substitution in u, so how do you know what to choose to replace with u? Well, this gets to what we did in pre-calculus a little bit, is function composition. Remember, you're looking for a function on the inside and a function on the outside. You're actually looking for that function on the inside, okay? Because remember, this is the opposite of chain rule. So you're kind of asking, well, what was on the inside before we did the chain rule? And here are just some hints. So if you have a trig of a function, your u is your input, or the angle of that trig function. So for example, if you get something like this, integral of sine of 2x dx, then your u will just be that 2x in there. Whoops. See how that's on the inside of the function, or the input. If you get something like this, where you have a square root inside a square root, or you have it inside of something that's raised to a power, okay, then your u is just going to be what's inside the parentheses or inside the square root. So in this example here, we have 2x minus 9 is inside this cube, so 2x minus 9 will be your u value, okay? Here we have e to the power, so if you have your variable in the exponent, u is just going to be what the power of e is. So if you have, for example, integral of e to the 7x, u is just 7x. And if you have a fraction, u is often the denominator, okay? So I kind of have it written there so you see that. And then you also want, if you have a situation where you have multiple exponents, you have no way to combine them, then you generally want to pick where u is the higher of the two powers, okay? Because if you think about it, when you're working backwards, taking the derivative, you'll chain rule and you'll get the lower derivative will be the other output, okay? But like I said before, sometimes you just have to be insightful and have perseverance, meaning you might just have to try multiple times, and that's what it's going to take on a lot of these, you guys. That's why we're getting started with this as soon as possible. So let's walk through this process, and I'll follow the steps 1 through 6 to show you what I'm doing in each step. So step 1 tells us to choose a u substitution. So I see a trig function here, and according to my tips, if we have a trig, just make u the input. So let's do that. So u equals x plus 9. Okay, so that is step 1. Actually, I'm going to zoom in a little bit here so Stuff gets a little bit larger, it's easier to see. Cool. All right. Step 2 is then to take the derivative. And derivatives get taken a little funny here. You'll recognize you'll be doing okay. But we're trying to find du because we have this dx here. And our ultimate goal is to replace that dx with du because you need all your things in terms of u if you're going to take an integral. So we take the derivative of u, we get du. Take the derivative of x, you get dx. And then this plus 9 just kind of goes away, right? Because it's plus 0, right? But I don't need to write that because the derivative of 9 is 0. So we are taking the derivative here. I'm going to write that down. So step 2 is we just took the derivative, d dx, okay? So we did that, and look, we already have dx solved. So in this case, it'll be a pretty straightforward thing that we're just going to substitute out. Instead of writing dx, we're going to write du because they're equal in this case, right? I chose a u that worked out really nicely there. You can't always do that, but here we can. So this step 3 is rewrite it in terms of u. So I'm going to do that. So instead of, I'm going to still leave the sign, but instead of x plus 9, I'm going to put u instead. So u. And instead of dx, I need to have du. Okay? Now this is an integral that we can do. Let's see, derivative of sine is cosine, so going the other way, we're going to get negative sine. So integration, the antiderivative is negative cosine of u. And we always want to write plus our constant plus c. Now, here's, we just integrated it. That was step 4. Step 5 is substitute it back in. So I can't leave it as u. I need this in terms of x because that's what my original problem is. So I'm going to write negative cosine, but instead of u, I'm going to replace it with what I said, or what we agreed u would be. So x plus 9. Keep your plus constant out there, and we are done. Now before I box this and say, hey, that's my answer, let's just check it real quick by taking the derivative and making sure that we had our original function. So this is step 6. So I take the derivative of this. Notice derivative of negative cosine will be positive sine, so we get sine. I'm going to follow a chain rule here, so I need to leave the inside alone. Then multiply by the derivative of the inside. Fortunately, the derivative of the inside here is just 1. So I can put times 1, or I don't need to put anything. And the derivative of any constant is 0, so look, I got my original integrand, and I know this is correct. So let's put a box around, see if we can get it, there we go. Box around my answer, because that is my answer. Negative cosine of x plus 9 plus c. So those are the 6 steps. I won't label the 6 steps from here on out, but I want to show you guys those. And what we'll do is, yeah, it gets a little more complicated just because we have to solve for dx, especially this step right here. We've got to make sure that we get dx by itself. It's not always as simple as simply saying, oh, look, they're the same thing. So let's move on and try this next one. Here, I mentioned if we have a square root, you want to pick u to be what's inside the square root. So let's do that. So here I've got u is 1 plus x squared. And now we're going to find du, so we take the derivative, and here's where it's important to remember we need to get dx. So derivative of 1 is 0, so we don't care about that. Derivative of x squared is going to be 2x, and of course we need to follow a chain rule here, so the derivative of the x on the inside, that's going to be dx there, all right? So we have our dx, and let's solve for dx, get dx by itself. So I'm going to divide both sides by 2x. I'm just going to write this on the side here. dx is equal to du over 2x, okay? I just divided both sides by 2x. Now that I have dx by itself, I can substitute dx out, and I can substitute u, 1 plus x squared for u. So let's do that. So we get integral of 2x, the square root of u. I'll substitute that out because I don't want any x's. And then instead of dx, I'm going to put du over 2x, because that's what I figured out is equal to dx here. So I can substitute that out. And now it's this step, I need to make sure all my x's, I get rid of them. And look, I have 2x divided by 2x, so I can actually divide those out. And I now have an integration without any x's. Perfect. Let's rewrite this in terms of, do I have space here? I think I got space. Yeah, I got space. Let's rewrite this in terms of u to the 1/2 power, just because that's a bit easier to integrate. And so now we can use our power rule. So let's add 1 divide by that same number. Don't forget to add our constant. And we get 2/3, but I don't want to leave it in terms of u. I need to put the 1 plus x squared back in here, and to the 3/2 power plus c. Let's just check this really quickly, making sure that I get my original integrand. So I'm going to take the derivative. Notice when I take the derivative, 3/2 comes down in front. 3/2 times 2/3 is 1. So that all goes away. I'm going to subtract 1 from up there. That's going to be 3/2 is 1/2. And then I need to remember a chain rule because I have 1 plus x squared. I need to take the derivative of the inside. I left it alone, and now I multiply by the derivative of the inside. Well, the derivative of that is going to be 2x. Derivative of c is 0. So I get this. Is this the same as what I started with? Well, yeah, look, it is. This 1/2 is that square root. The 2x is outside, and 1 plus x squared is on the inside. So my answer was actually this one right here. Let's box that. I just checked it to show that when we take the derivative, we get our integrand in the original. Alright, moving on, let's do this one very quickly. We should be able to pretty quickly here. Because I see parentheses, something to a power. The inside is going to be my u. Let's try that out. So take the derivative, du. Derivative of x is dx. Derivative of negative 8 is 0, so I don't need to worry about that. Hey, I got something where I can simplify and solve this real quick again. So let's substitute. So we get u to the 23rd power. Instead of dx, we get du. Now we can take the derivative. So add 1, divide by that number, and add your constant. Now, I need to substitute this back in, so I'm going to have x minus 8 instead of u to the 24th power, all divided by 24 plus c. And at this point, I'm going to kind of stop writing down the check, okay? You can kind of eyeball this and see, all right, if we took the derivative, 24 would come out in front. 24 divided by 24 is 1. So we get x minus 8 to the 23rd power. That's what we started with, so we're good. All right, a few more to do here. Here, I notice I have a trig, so I'm going to make a guess and say, let's try to make u be the input for this trig function, okay? So we get u equals x to the 4th power, okay? It might not work out, but it might, we'll see. So let's take the derivative, so we get du equals, derivative of this is 4x cubed, but then we do chain rule, so then we also multiply it by dx, because the derivative of x is dx. So we get this, and we need to solve for dx, so I'm just going to divide both sides by 4x cubed. Dx is du over 4x cubed. Okay, cool. So now that I got dx, I can plug these in. So let's plug them in, so I get x cubed cosine of, well, I want u to be on the inside. And instead of dx, I have du over 4x cubed. Well, look at this. The x's, x cubed and x cubed, that gets divided out. We don't lose all of it. You see there's still a 4 divided by 4 there, right? Or 1/4. So I could rewrite this as the integration of 1/4 cosine of u du. It might be a little bit easier to integrate there. But I got rid of my x's. That was my goal, right? So we can go ahead with step 4. So let's integrate that. Oh, I'm running out of room here. Let's see here. Integration of cosine. We have sine. So I have 1/4 is still out in front. Sine of u plus c. And then, of course, I need to substitute out u. So we get sine of x to the 4th plus c, and we are done. You can think about it. If you take the derivative of sine is cosine, so we got that part. This x to the 4th, we need to use chain rule, so we will get 4x cubed. Well, the 4 times 1/4 is 1. Leaves us an x cubed out in front, so we are good to go. All right. For this one, I see input is 5x. I'm going to make u be 5x. Here, because it's the input both places, I'm going to substitute that out when I go into substituting it. But let's just take the derivative. Derivative of 5x is going to be 5 times dx. So when I solve for dx, I get 1/5 u, du. And now I can substitute this in, so let's get integral of secant of u, tangent of u. Dx is going to be 1/5 du. Notice we have secant tangent. That's one of the things directly from our sheet because the derivative of secant is secant times tangent. So when we integrate it, we get secant of u. I do have the 1/5. I can put it out in front or behind, either way, doesn't matter. And then we need plus our constant. And yeah, but we need to substitute this back in. Well, we get u is 5x, so 1/5 secant of 5x. And there we go. Imagine taking the derivative. Derivative of secant is secant tangent. You're going to leave the 5x on the input of both of those functions, but you will use chain rule. Derivative of 5x is 5. The 5 times 1/5 means there won't be any coefficient. So we got that one correct. All right, moving on. My voice is going. No. We get the integral. Oh, we're not. Why am I writing integral? U. What is u? Well, inside of this power function, of course, right? So u is going to be 2x plus 3. Let's take the derivative and see what happens. Du. Derivative of 2x is going to be 2 times dx. Derivative of 3 is just 0, so we leave that part alone. So when we solve this, we get dx, or solve for dx, we get dx equals 1/2 times du. Notice I prefer writing them as fractions. You could write du over 2, but when you go back to substitute it back in, it's a little easier to move the fraction around. So just a little tip there. So let's now substitute stuff in. So we get the integral of, instead of 2x plus 3, we write a u. Instead of dx, I'm going to write 1/2 du. And now we take the integral of this, so we're going to do u add 1, divide by that number, 10. The 1/2 I can just bring out in front, and we need to put plus c. Well, I can't leave it as u, right? I need to substitute this back in, so we get 2x plus 3. So it is 2x plus 3, all of that to the 10th power, all divided by 20. And don't forget plus c. So that is our answer. Boxing it with this funny shape box. You take the derivative of that and you would see, yes, you get the original answer again. Good practice to do that. I want to move on for the sake of time. Alright, here we've got a square root, so I'm going to make u be the inside of that square root and see what happens here. Let's take the derivative of both sides. Derivative of 1 is 0. Here we get negative 2 dx. So when I solve for dx, I'm going to get negative 1/2 times du. That'll be good, because now we can write down the integral. So we get square root of u times negative 1/2 du. Now instead of square root, I'm actually going to write to the 1/2 power. That will help with the when we take the integral. So let's go and take the integral. So u add 1, divide by that, multiply. We already have the negative 1/2 out in front, and don't forget to add your constant. Let's see here. When we do this, we get dividing the same as multiplying by the reciprocal. So I'm going to flip that. And I should have got, well, yeah, I'm just writing this down quickly. Let's simplify this here. The 2's divide out, right? So we end up getting negative 1/3. But I do need to substitute out this u, and I need to put 1 minus 2x there instead. So we get 1 minus 2x to the 3/2 power plus c. All right. Last two here, I believe. Yep, last two. So we have a power here, so that 5x is going to be our u. Take the derivative. You get 5 du. So when we solve, oops, not du, dx. So when we solve for dx, the dx from somewhere, the dx becomes 1/5 du. I like that fraction there. So here we go. Let's substitute this in into our integral. E to the u. And then we get 1/5 times du. So e to the u, well, e to the u is just e to the u, right? When you take the integral or the derivative. And that 1/5, we can write it down in front. But the du goes away once we integrate. So we get 1/5 e to the u plus c. Well, let's just check and make sure this is right, because, oh wait, we're not done yet. We do need to substitute it back in. Remember I said the most commonly missed item. U is 5x, so let's just put a 5x there, and that is plus c. Let's check and make sure this works, though. When you take the derivative, I'm prematurely boxing it there, take the derivative, e to the 5x, we need to follow chain rules. So you get e to the 5x, bring the 5x down in front, or you're multiplying with the derivative of it, rather, so that's really 5. Well, 5 times 1/5, that's 1, so that goes away, so you end up getting what we started with. So it works. And last one here, perhaps the most complicated, though nothing too bad yet. I do see a denominator, I see a fraction on the inside, I see something on the inside with parentheses. Let's make the inside of those parentheses be our u, okay? So I'm going to plug, make u be 1 plus 5x. You could try 1 plus 5x cubed, but I don't think it'll work out very well for you. And besides, we can take the integral of u to the third power, right? And when it's the denominator, we'll see in just a second. So let's do this. This seems like a good first step. Derivative of 1 is 0. Derivative of 5x is 5 dx. So when you solve, whoops, I want to draw in dashes there, not there. When you solve for dx, you get 1/5 du. So now let's substitute out the dx and substitute out that on the inside. So we get 2 over u cubed. Instead of dx, it's going to be 1/5 du. Well, we can't take the derivative as it is. We need to bring this u out in front, up above, right? So I'm going to instead rewrite it 2/5 u to the -3rd du. And we can integrate this. So we get 2/5 add 1. Divide by that number and add a constant. We do have 2's we can divide out. So our final answer is going to be 1 over 5u squared. But instead of u squared, we need 1 plus 5x squared. So 1 plus 5x is what we're going to do to replace that. So instead of the u, we put 1 plus 5x, and we get that right there. So hopefully this is a good start. You guys can do your textbook problems, and we'll help you guys out with that tomorrow. Thank you guys for watching.